Hello and welcome to the third introduction video to Laplace Transformation Table of Standard Values. So as I already said in the first video, we have about seven table of standard values, and in the first two videos we've highlighted 5 of them, remaining 2. So this video will target the remaining 2 table of standard values. Now the sixth, which I will continue in this video, or the first, which I will call the sixth in this video, of the table of standard values are the Laplace transformation of hyperbolic sine function, and the seventh is the Laplace transformation of hyperbolic cosine function. So let's start with the sixth, which is the Laplace transformation of hyperbolic sine function, simply called the sine function. Now let's say we are given f of t to be equal to sine at, where a is a constant, and we are asked to find the Laplace of this function. Now we already know that the Laplace of this function, or Laplace of any function f of t, is simply given as integral from 0 to infinity the function f of t multiplies exponential minus st dt. So this is the formula to calculate Laplace transformation for any given function. All right, now the function is a hyperbolic sine, so we simply put in Laplace of sine at, and this is equal to integral from 0 to infinity. In place of f of t now is sine at, we simply append sine at, then put down exponential minus st multiplied by dt. You simply have this. Again, you're having two functions multiplying one another, which means you're going to be employing the integration by part, which is product integration. And to calculate the integration by part for any given function, we simply make use of the formula integral of u dv is equal to uv minus integral of v du. This is how you calculate or solve for product integrations. Now I said that u always should be the function given to you, whereas dv, okay, dv remains exponential minus st dt, okay, which is the function from the Laplace transformation. Okay, so we simply call u to be the function given to you, and the function given to us is f of t. In this case is sine at, so u is simply sine at, whereas we say let the v be the Laplace exponential function. So we have that dv is equal to exponential minus st multiplied by dt. Now from the formula you have uv minus integral of v du, so which means you need to find du, you also need to find what? V. To find du simply means differentiate the value of u. So you simply have that u is sine at. Now to differentiate sine at, I've always said to differentiate a trigonometric function, the first thing to do is differentiate the angle, use that derivative to multiply the derivative of the trig function itself. Now you have to be very careful in this case. This is a hyperbolic trig function. So if I differentiate sine or sine, I'm simply going to have cos. The same thing happens if I differentiate cos. Instead of having minus sine, I will simply have plus sine, because the derivative of a hyperbolic function remains positive, it doesn't change. All right, so du is equal to, the angle in this case is at, and if I differentiate at with respect to t, I'm simply going to have a. Use this derivative a to multiply derivative of what? Sine. If I differentiate sine, I will simply have cos. Then you put back your angle. That means du becomes a cos at. Now, since I differentiated u with respect to t, I will simply append dt here. So this becomes du equals a cos at dt. Now, to obtain v from the formula, of course, it says uv. So we need to find v. To find v, we simply what? Integrate the v, which means we have to integrate this exponential function here minus st dt. And to integrate an exponential function, I've always said the first thing to do is differentiate the power of the exponential function, use that derivative to divide the exponential function itself. For instance, the power of that exponential function there is minus st. If I differentiate this function with respect to t, I will be left with what? Minus s. Hence, use this minus s to divide the exponential function itself. So I'm simply going to have exponential minus st all over minus s. This becomes the derivative, this becomes the integral of that function. Okay, so I can easily rewrite this as what? Taking this negative sign up, it becomes minus exponential minus st all over s. So this becomes the integral of that function. Hence, v is simply equal to, therefore, v is simply equal to minus exponential minus st all over s. Now, we have these values for v and we have the value for dv. We can simply now plug it into the integration by parts formula. Now, from the formula, we have integral of u dv. So you put it down, integral u dv, and that's simply equal to, remember the formula, u times v, and u is what? Sine 80. So you put it down, sine 80 multiplied by v, and v is simply given as this, minus exponential minus st all over s minus integral of, okay, integral of v times du, and v once more is this. So you have minus exponential minus st all over s times du, and du simply gave us a cos 80 dt. So you simply have a cos 80 times dt. You have this. Okay, so you have integral of u dv to now be equal to, now rearranging this a bit, I can simply have minus exponential minus st sine 80 all over s, minus times minus here becomes plus. Again, I have a as a constant, I have s here also a constant, I can pull them out. This becomes a all over s integral of, let me rearrange this a bit now. This gives me cos 80 exponential minus st times dt. Okay, now this simply means I still have to integrate this part of the equation further. Since I'm having an integral sign there, it means I still have to integrate this further. Now this is also a product integration, cos 80 multiplying exponential minus st dt. So which means we're still going to employ the integration by parts formula to solve this. Now I'm going to be doing this together. Okay, I will just do this integral at once, but still obeying the steps. Okay, now I'm going to have integral of u dv to be equal to minus exponential minus st sine 80 all over s, which is this, plus a all over s. Now I have to repeat this integration since this is also integration by parts. Now remember, always consider u to be what? The function given to you. In this case, u becomes cos 80 and the v remains exponential minus st dt. So this part remains the v, whereas this remains u. Now from the formula, that integral is simply what? U times v. And what is v? V is obtained by integrating exponential minus s dt. Okay, if we did that over here and we had minus s minus exponential minus st all over s, so this is always going to be our v. Okay, but u in this case now, u becomes cos 80. So obeying the formula, u times v, so we have u as cos 80 times v, v remains minus exponential minus st all over s minus integral of v du. Now what is v? Once more, v remains minus exponential minus st all over s multiplies now by du. Now we said let u be what? Cos 80. Now if u is cos 80, then we need to find du. To find du, again, you're differentiating a hyperbolic trig function. First thing to do is differentiate the angle. The angle is 80. If I differentiate 80, I will simply have a. Use this derivative to multiply the derivative of the hyperbolic cos. Now mind you, if you differentiate cos, you're going to have sign, positive sign, and not a negative sign. Please keep that in mind. If you differentiate hyperbolic cos, you have it to be a positive hyperbolic sign and not negative. So which means derivative of cos 80 will simply give me sine 80. All right, so that means du is equal to a sine 80. But since I differentiated u with respect to t, you always append the t there. That means for this part which says integral of v du, okay, du now becomes what? The whole of this, a sine 80 times dt. So in place of that, we simply have a sine 80 times dt. All right, so we simply have that. Okay, so integral of u dv is now equal to minus exponential minus st sine at all over s. Let's now expand. Okay, let's rearrange what is inside this bracket. So this remains plus a all over s into, rearranging this, we have minus exponential minus st cos at all over s. Now, mind you, minus times minus here becomes plus. A is a constant, s is also a constant. You can put them out, so you have plus a all over s integral of integral of sine at exponential minus st times this dt. Now we can expand with this term outside the bracket. Hence, integral of u dv is equal to minus exponential minus st sine at all over s. Expanding with a over s here, a multiplies everything here, s multiplies what is at the denominator here. So we simply have minus a exponential minus st cos at all over s times s here gives us s all squared. Similarly, a multiplies a here gives us plus a squared all over s multiplies s gives us s all squared integral of sine at exponential minus st multiplied by dt. Now let's plug in all constants or functions and their notations. I have integral of u dv. Let's move from beginning. From the beginning, I said let u be equal to sine at and let dv be equal to exponential minus st dt. So which means in place of u, we can put this back. This becomes integral. In place of u, we call u to be sine at and we call dv to be exponential minus st times dt, and this is equal to this result to obtain here, minus exponential minus st sine at all over s minus a exponential minus st cos at all over x squared plus a squared over x squared integral of sine at exponential minus st times dt. Now, having this now, we can now compare the both equations. Observe that at the left-hand side, we have integral of sine at exponential minus st dt, and on this part of the right-hand side, we still have that same integral repeating itself, integral of sine at exponential minus st dt, which means both of them are the same thing. So at this point, what you do is not to further integrate this part. Rather, since this is what we are looking for, you bring this part over to this side of the equation, let both of them meet. So you simply what? Collect like terms. Collecting like terms, now you have, putting this down, this becomes integral of sine at exponential minus st dt. Now, this is positive a squared all over x squared. So if this cross over, it becomes negative. Positive sign cross and equal to sign becomes negative. So I have minus a squared all over x squared integral of sine at exponential minus st dt, and this is now equal to this result left. So we have just these two results left, which is minus exponential minus st sine at all over s minus a exponential minus st cos at all over s all squared. So I have this. All right, let's continue the integral here. All right, so we simply have, now at this point, one of these integrals, of course, we can factor one of these integrals since it is common. We can simply factor out one. So we have integral of sine at exponential minus st dt is now common into, it becomes 1 minus a squared all over x squared. And this is equal to this result, minus exponential minus st sine at all over s minus a exponential minus st cos at all over x all squared. So we simply have this. Now, what we'll do at this point is rearrange these terms in the bracket. I'll have integral of sine at exponential minus at. If I rearrange these terms in the bracket, of course, this one can also be written as 1 divided by 1. So the LCM between the two of them is simply x squared. X squared divided by 1 becomes x squared. X squared times 1 gives me x squared minus x squared divided x squared is 1. 1 times a squared here gives me simply a squared. And this is equal to everything here. So I have minus exponential minus st sine at all over s minus a exponential minus st cos at all over x all squared. Now, at this point, we can simply find our integral by dividing through with what? X squared minus a squared all over s squared. And I've said in the previous videos, if you carry out this division, the order of this, the arrangement of these terms in the bracket will change over this other side of the equation. So this makes now integral of sine or sine at exponential minus st dt becomes, this is now equal to, upon division, this sign goes, this particular part or this variable x squared goes up, whereas this other variable top comes down. All right, so I will simply have x squared all over x squared minus a squared, okay, upon division. Now the whole of this is multiplying everything here. We have minus exponential minus st sine at all over s minus a exponential minus st cos at all over x all squared. So we have this. All right, so the integral of sine at exponential minus st dt is now equal to, so we simply expand the bracket with this term. Now, this multiplied by this, I have over x here. X cancels one of the x here. So I'm left with x at this numerator. So x multiplying this term becomes minus exponential minus s exponential minus st sine at all over, whereas at denominator I'm now left with what? X squared minus a squared. Okay, minus same thing now. This term multiplies this other term. X squared here cancels this x squared. So I'm simply left with what? A exponential minus st cos at all over. At the denominator, I'm left with x squared minus a squared. All right, so having obtained this, the next thing now, the Laplace transformation of that function can only be found when we put in the limits. So we need to now effect the limit. And the limit is simply from 0 to infinity. So effecting the limit from 0 to infinity, all right, from 0 to infinity, you simply have this. Hence, okay, effecting the limit now, we are going to be having, wherever you see t, let's start with the upper limit. Put in the upper limit first minus the lower limit. Now we're starting with the upper limit. Whenever you see t, you put in the upper limit. Upper limit remains infinity. So we start with this function here. This is now minus se exponential st. In place of t, we put in what? Infinity. So it becomes exponential minus infinity times s. Okay, sine at. In place of t becomes infinity. So it becomes sine infinity times a all over x squared minus a squared minus the term we have here. This is a exponential minus st. In place of t again, put in the infinity sign. It becomes minus infinity times s. Okay, now cos at, but t there is infinity, so cos infinity times a all over x squared minus a squared. So this is the upper limit. Now, upper limit minus the lower limit. For the lower limit, you simply have 0. So which means wherever you see t, put in the value as 0. So we start afresh. This is minus s exponential minus st, but t now is 0. So 0 times x is 0. 0 times minus sign is 0. So we simply have exponential 0 sine at. T now is 0. 0 times a is 0. So we simply have sine 0 all over x squared minus a squared minus a exponential same thing minus a exponential minus st. T now is 0. 0 times x is 0. 0 times minus is 0. So it becomes exponential 0. Okay, cos. We have cos at. T is 0. 0 times a remains 0. So we have cos 0 all over s squared minus a all squared. So these are the lower values at the lower limits. All right, so integral from 0 to infinity of sine at exponential minus st dt is now equal to, so let's find the values of this limit. Exponential to infinity is undefined, so it's usually considered 0. The sine or the hyperbolic sine of a function to infinity is also undefined, hence we consider the whole of this as 0. Similarly, the cosine of hyperbolic function to infinity is also considered undefined, hence it becomes what? 0. And here I have sine 0. The sine of a hyperbolic function at angle 0 does not exist, is 0. So we also consider the whole of this as 0. So which means this gives us actually 0 minus, we have 0 minus, okay, the first part here is also 0. So this is simply 0 minus, okay, 0 minus. Now let's watch out the other part. In this case, I have exponential 0 is 1. Of course, any variable to the power of 0 remains 1. So exponential 0 is 1. Cos 0 is also 1. Okay, cos 0 is also 1. So you simply put in that value. This becomes, okay, cos 0 is also 1. So 1 times a remains a all over x squared minus a squared. So you simply have a all over x squared minus a all squared. All right, so the integral from 0 to infinity of sine at exponential minus st dt is now equal to 0 minus 0 is 0. Of course, we have a minus sign there, so this is literally off. It becomes 0 minus minus a over x squared minus a squared. Minus minus becomes plus, so this becomes a all over x squared minus a squared. Hence, the Laplace of hyperbolic sine of a function, sine at, is automatically given as a all over x squared minus a squared. So this is the sixth table of standard value you need to know in Laplace transformation. The Laplace of a hyperbolic sine function or sine function is simply a all over x squared minus a squared, where a becomes the number or the constant in front of the trigonometric function. Now, let's say you're asked to find the Laplace of sine 5t. Laplace of sine 5t becomes automatically 5 all over x squared minus 5 all squared. So this is actually 5 all over x squared minus 5 squared gives you what? 25. You simply have this. Also, if you're asked to find Laplace of sine 6t, it's simple. From the formula, it is simply what? 6 all over x squared minus 6 all squared. So this is actually 6 all over x squared minus 6 squared will give you what? 36. We simply have this. All right, so that becomes the sixth table of standard values you need to know in Laplace transformation. All right, guys, so let's consider the seventh, which in this case is the last table of standard value for Laplace transformation, and it's simply the Laplace of hyperbolic cos function, which is simply called cos. So simply the Laplace of cos function. So let's say we are given a function f of t to be equal to cos. In this case, let's use a real number. It's supposed to be cos at, but let's attach a real number to it. So simply call it cos 5t. Let's simply say a there is equal to 5. So we're simply working with cos 5t. Let's solve this Laplace transform and see. Hence, we have to find the Laplace transform of cos 5t. Now, this is equal to, from the formula, integral from 0 to infinity, f of t is cos 5t. So we simply have cos 5t multiplied by exponential minus st times dt. So this is the Laplace transformation. Now, again, this is the product of two functions, so we simply employ integration by parts. We already know integral of u dv is equal to uv minus integral of v du. It's as simple as this. Now, I always say let u be the function given to you. In this case, function given to us is what? Cos 5t. That's the given function, f of t. Hence, u is equal to cos 5t. And always dv remains the Laplace function, exponential function, in this case, exponential minus st times dt. Okay, so we need to find from the formula, we need to find du. We also need to find what v is. Du simply means differentiate u. If I differentiate u, remember to differentiate a trig function, first of all, differentiate the angle. The angle there is 5t. If I differentiate 5t, I'm simply going to have what? 5. Okay, then again, you differentiate the hyperbolic cos. Mind you, derivative of hyperbolic cos will simply give you plus sine and not minus sine. So keep it in mind. Now, if I differentiate cos, I will simply have sine, put back your angle, which is 5t. Then I simply said use this derivative now of the angle to multiply the derivative of the trig function. The derivative of angle gave us 5, so this is simply 5 sine 5t. And since we differentiated this function with respect to t, you simply append the t to it. Hence, the u becomes 5 sine 5t times dt. This simply gives me the u. And v is obtained by what? Integrating the v, which means integrate this function. We've done this earlier. The value remains minus exponential minus st all over s. So we simply have this. So we plug this back now into the integration by parts formula. This is integral of u dv, and that's simply equal to, so we said uv, and what is u? We said let u be equal to cos 5t. So in place of u, you have cos 5t times v. V is equal to minus exponential minus st all over s minus integral of v du. What is v again? V is minus exponential minus st all over s times du. Du gave us 5 sine 5t dt. So we have 5 sine 5t times dt. All right, so integral. Okay, let's pull this up. So we simply have integral of u dv to now be equal to, okay, so we have, rearranging that now, we are going to have minus exponential minus st cos 5t all over s. Mind you, minus times minus here becomes plus. 5 is a constant, s is a constant, so pull them out. I will simply have plus 5 all over s integral of sine 80 sine 5t exponential minus st times dt. Okay, so this simply means I still have to integrate sine 5t exponential minus st dt. All right, so I still have to integrate this function. By so doing, I'm still going to be employing all principles of integration by parts, which I have done so far. So this is minus exponential minus st cos 5t all over s plus 5 all over s into, now let's integrate this function. So I'm going to be going very direct. Okay, so you try to catch up with me, but you see the same procedure. So always u represents the given function. In this case, u is simply sine 5t, whereas dv always represents exponential minus st dt. So from the formula, u times v, what is u? U is sine 5t in this case, so we have sine 5t times dv. dv is exponential minus st dt. Okay, so it's simply uv. So we need to find v by what? Integrating dv, and we had it to go minus exponential minus st all over s. So from the formula, v is now minus exponential minus st all over s minus integral of v du. Integral of v du, v once more is minus exponential minus st all over s times. Now we said u is sine 5t. That means if u is sine 5t, then du is equal to, remember, differentiate the angle. 5t is the angle. If I differentiate 5t, I will simply have 5. Differentiate sine, I'm going to have cos. Then put back your angle 5t. Now, since I differentiated with respect to t, you simply multiply by what? The t. Okay, so this will give us 5 cos 5t times the t. All right, so we have this. Okay, so integral of u dv is now minus exponential minus st cos 5t all over s plus 5 all over s. Let's rearrange these terms in the brackets. So we are simply going to have minus exponential minus st now sine 5t all over s. Mind you, minus times minus here is plus. 5 is a constant, s is a constant, pull them out. This becomes plus 5 all over s integral of cos 5t exponential minus st times dt. So we can now expand with 5 over x. This gives us integral of u dv to be equal to minus exponential minus st cos 5t all over s. Alright, so 5 over s multiplies minus exponential minus st sine 5t over s. This will give us minus 5 times exponential minus st sine 5t all over s. Okay, so s times s gives us s squared, so all over x squared. Similarly, plus 5 times 5 here is 25. All over s times s here gives us s squared. Integral of cos 5t exponential minus st times dt. Alright, so at this juncture, let's plug in all symbols and their notations. We said let u be equal to cos 5t and dv be equal to exponential minus st dt. And here I have integral of u dv. So this is now integral u. We said let u be simply cos 5t and dv be exponential minus st dt. So this is equal to the whole of this. We have minus exponential minus st cos 5t all over s minus 5 exponential minus st sine 5t all over x squared plus 25 all over x squared integral of cos 5t exponential minus st times dt. Alright, so we have this. So comparing the left hand side and the right hand side, notice that this integral cos 5t exponential minus st dt also appear there, and this is what we are looking for. So there is no need to further what integrate this function. Hence, all we need to do is to what bring it closer to this one by collecting like terms. So let them be on one side. So you simply collect like terms and send this man over here, since this is what we're looking for. So we have now integral of cos 5t exponential minus st dt. Okay, so this is positive. If you cross over this equal to sign, it becomes negative. So we have minus 25 all over x squared integral of cos 5t exponential minus st dt, and the whole of this is now equal to these two results, minus exponential minus st cos 5t all over s minus 5 exponential minus st sine 5t all over x all squared. Okay, so comparing these two now, of course, we can factor out one of these integrals since they are common. We can simply factor out one, so it becomes integral of cos 5t exponential minus st dt into 1 minus 25 all over x all squared. Now this is equal to minus exponential minus st cos 5t all over s minus 5 exponential minus st sine 5t all over x all squared. All right. Let's continue over here. So we have integral of cos 5t exponential minus st dt into, so let's rearrange now this term. Okay, we have 1 minus 25 over x squared. So this one can also be written as 1 divided by 1. The LCM there becomes now x all squared. So x squared divided by 1 is x squared multiplied by 1 here gives us x squared minus, of course, x squared divides x squared is 1. 1 times 25 gives us 25. And this is equal to minus exponential minus st cos 5t all over s minus 5 exponential minus st sine 5t all over x all squared. Okay. All right. So in order to make this integral subject, it means we have to divide both sides by what? S squared minus 25 divided by s squared. And I've said earlier that if you divide by this term, on this side of the equation, the order of arrangement of this term in the bracket will change. Hence, we are going to have integral of cos 5t exponential minus st dt to now be equal to, upon division, I will have x squared going up. It becomes x squared all over x squared minus 25. And the whole of this multiplies everything here. We have minus exponential minus st cos 5t all over s minus 5 exponential minus st sine 5t all over x all squared. Okay, we have this. So let's expand now with this term. This will give us integral of cos 5t exponential minus st dt to now be equal to, now take note, I have x squared here multiplying this term, but there is x here, so x here cancels one of these x and left is just one x here. So this multiplied by minus exponential becomes minus s exponential minus st cos 5t all over, as the denominator I will have x squared minus 25. Okay, minus same thing. Now if this multiplies this, I have x squared here, this x squared cancels this x squared, so I'm simply left with 5 exponential minus st sine 5t all over x squared minus 25. Okay, so at this point, this can now become a Laplace when we would impute this limit from 0 to infinity. Hence, we have to now effect the limit from 0 to infinity. Simply effect the limit from 0 to infinity. So if you're effecting the limit now, upper limit start with infinity, lower limit, upper limit minus lower limit. So wherever you see t in this equation, simply put in the upper limit and then later on put in the lower limit. So let's start with the upper limit first. This will give us minus s exponential minus st. In place of t, we'll put in the upper limit infinity. They become minus infinity s, okay, cos at and in cos 5t, and in place of t, we'll put in infinity. So this becomes infinity times 5 all over x squared minus 25. Okay, minus, I have here 5 exponential minus st. Again, in place of t, we'll put in infinity, so it becomes minus infinity s. I have sine at or sine 5t, sorry. So in place of t, t is infinity, so it becomes sine infinity times 5 all over x squared minus 25. So this is the upper limit minus the lower limit. Lower limit now is 0. So wherever you see t, you put in the value as 0. Okay, so we start afresh. I have minus s exponential minus st. T now is 0. So t times x, which is 0 times x becomes 0. 0 times minus becomes 0. So I have exponential 0 cos. Again, I have cos 5t. T is 0. 0 times 5 becomes 0. So it becomes cos 0 all over x squared minus 25. Minus 5 exponential same thing. Exponential minus st. T is 0. So 0 times everything here becomes 0. So I have exponential 0 sine 5t. T is also 0. So it becomes sine 0 all over x squared minus 25. Okay, so I said earlier, the exponential function to infinity is undefined, and hyperbolic cos to infinity is also undefined. So automatically everything here becomes 0. Same thing as well, everything here becomes 0. So the integral from 0 to infinity of cos 5t exponential minus st dt is now equal to everything here is 0 minus. Next up, exponential 0 is 1, cos 0 is also 1. 1 times minus s simply gives us minus s all over x squared minus 25. Okay, minus. Similarly, sine to 0 of course is 0, so which means everything here is 0. So I have here to be 0. So minus times minus x all over x squared minus 25, minus times minus becomes plus. This simply means that the Laplace transformation of cos 5t is actually equal to what? S all over x squared minus 25. And this is actually s all over x squared minus, remember the value in front of the hyperbolic cos function is what? 5. So, and we are having 25 here. So, which means this 5 was actually what? Squared. So, it becomes 5 all squared. Hence, the Laplace of cos at, Laplace of hyperbolic cos of any function is simply given as what? S all over x squared minus a squared, since a is the number or the constant in front of the hyperbolic cos. So we simply have s all over s squared minus a all squared. So this is how, or this is the last table of standard value for the Laplace transformations. Let's pick one or two examples to explain all of this, okay? All right, so let's say we are asked to find the Laplace of cos 3t is simple. It becomes s all over x squared minus 3 all squared. So this is equal to s all over x squared minus 3 squared. There is what? 9. That becomes the Laplace of that function. Similarly, if you're asked to find the Laplace of cos, let's say 10t is simple. It becomes s all over x squared minus 10 all squared. So this is simply equal to s all over x squared minus 10 squared. There will simply give you what? 100. All right, so that becomes the Laplace transformation of that given function or of a hyperbolic function considering table of standard values. So in all, we've talked about 7 table of standard values which we are supposed to use when considering or solving any problem involving Laplace transformation. The very first, I said it is the Laplace transformation of a constant. If you're asked to find Laplace of a constant a, it is simply what? A all over s. Hence, if you're asked to find the Laplace of, let's say, 5, this is simply what? 5 all over s. Laplace of any constant becomes that constant divided by x. The second standard value I talked about is a Laplace transformation of an exponential function. Let's say exponential a t. Okay, we said this is going to give us 1 all over s minus a. Okay, the Laplace of exponential function, okay, exponential at is simply what? 1 all over x minus a. So if you're asked to find the Laplace of exponential, let's say 3t, this is simply equal to what? 1 all over s minus 3. Without you having to solve, this becomes a standard value. It is something you need to know, because when we start solving problems involving partial fractions and differential equation with Laplace transformation, you're expected to know the standard values. The third is the Laplace transformation of a function, okay, raised to an integer n or a number. So if I have to find Laplace of t to the power of n, I said it's going to be what? N factorial all over s to the power of n plus 1. Okay, hence, if you're asked to find the Laplace of t to the power of 3 or t to the power of 2, it is simply going to be what? 2 factorial all over s to the power of 2 plus 1. And 2 factorial remains 2 all over s. 2 plus 1 remains what? 3. That becomes the Laplace of a constant or a function raised to a constant or an integer. The fourth is the Laplace transformation a of three functions involving, let's say, sine. Okay, sine 80, Laplace transformation of sine 80, we simply obtain this to be equal to a all over x squared plus a squared, where a is a constant or number in front of the trig function. So if you're asked to find Laplace of sine 3t, this is simply what? A represents the number or the constant in front of the trig function, in this case now 3. So you simply have 3 all over x squared plus 3 all squared. So this will give you what? 3 all over x squared plus 3 squared is what? 9. That's how to find the Laplace transformation of what? Sine 80 or a trigonometric function. The fifth is what? Also Laplace of a cos function. So if you have to find Laplace of cos 80, this is simply going to be s all over x squared plus a all squared. So if you're asked to find the Laplace of cos 3t, is now equal to s simply all over x squared plus, now the a squared there becomes the number there, which is now what? 3 all squared. So this is actually s all over x squared plus 3 squared is what? 9. You have that. The sixth one is the Laplace transformation of hyperbolic function or hyperbolic sine. So let's say we're asked to find the Laplace of sine. Okay, sine 80. We've done this here and we obtain the value to be what? A all over x squared minus a all squared. Hence, if you're asked to find the Laplace of sine 3t, it is simply what? A there is a number, it becomes 3 all over x squared minus the number, which is 3 all squared. This will give you 3 all over x squared minus 9. That's how to find the Laplace transformation of a hyperbolic function. Finally, the seventh one is the Laplace transformation of cos 80, and this actually gave us s all over x squared minus a all squared. Hence, if you're asked to find the Laplace of, let's say, cos 7t, this is actually what? S all over x squared minus 7 all squared, which will give you s all over x squared minus 49. So these are table of standard values which you need to know. As we proceed in Laplace transformation, I'm going to be using all of this. So do well to watch the 3 introduction video for proper understanding of all the 7 table of standard values. I will see you in the next video. In the next video, we are going to be talking about inverse Laplace transformation. Okay, we are going to be talking about inverse Laplace transformation. I will see you in that video. Thanks and cheers.